Registration is open for our 111th annual meeting. This year's meeting will be held on November 4th through 6th in Tucson, Arizona, and it will be broadcast online in order to provide an interactive experience for both in-person and online attendees. If you would like to present at the meeting or provide an online research poster, please take note that the deadline for abstract submission is tomorrow. So please submit your abstract proposal as soon as possible if you haven't already got that in. This year, we are also holding a workshop titled Advanced Astro-Image for Exoplanet Observing that will be instructed by Dennis Conti, the leader of the AAVSO Exoplanet Observing section. The workshop will take place on November 7th and is exclusive to AAVSO members who will also be attending the 111th annual meeting in person. Due to the very hands-on nature of the workshop, it is limited to a maximum of 20 people. So if you're interested, we recommend registering as soon as you can. All right, next, we would like to thank and acknowledge our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, our favorite, astronomy. All right, now, usually we would be getting pretty close to the time where I introduce our speaker and stop talking. However, today I happen to be the speaker. How about that? So I guess I need to introduce myself. I'm a part-time contractor for the AAVSO. I get to do really fun work like schedule webinars and host them and help out with the AVSpec database. I also work a job new this year as an assistant for a professor at MIT, Professor Sarah Seeger. And it's a really cool job because I get to use Python every day to do all sorts of cool astronomy stuff. So I do have a bit of experience using Python. I taught myself back in 2020, right as the lockdowns were starting. And I found that you don't have to be an expert in order to get a lot of benefit in whatever your astronomical pursuit is. And I would like to share some information with you guys so that you can all start down that path if you're interested in yourselves and start learning Python and improve your astronomy. So let me go ahead and switch my screen share over to a more informative presentation view. 1 second here. Okay. So here's how we're going to get started today. There we go. Hopefully y'all can see my screen okay. If you can't, someone tell me in the Q&A. We're going to get started by talking about how it is you should set up Python. You've hopefully already done this, but in case you haven't, I'm going to show you where you can find some information on that to get started. So right now, our Python guide can be located on the 2022 How To Hours page. So to get there, you'll just go to aavso.org/2022 How To Hours, and that's separated by dashes. So going there, if you scroll down a little bit, you'll see some information about this webinar, and there is a link here to our preparatory guide, Introduction to Basic Python. So I'm going to go ahead and click on that link And that brings us to a PDF guide. Now, this guide covers a lot of the same stuff that we're going to cover today. So if you are left a little bit lost after today's presentation, my first recommendation to you would be to go and read through this guide, since you can move at your own pace. Now, the first section of this guide talks about installing Python. And as it turns out, installing Python is very simple. Now, if you had told me this when I was first learning Python, I would not have believed you, because installing Python was a nightmare for me. But I'll tell you why that is. It's because I was following some guides that were unnecessarily convoluted. Perhaps they would have been great for someone who is already an expert in Python and wanted to add some extra special configuration to their Python setup. But I was not that. I was just a beginner, so I didn't know what I was looking at. So when I Googled how to install Python and I looked at the guide that came up, it was not at all what I needed. So I've written down here the most simple method, okay, 4 very simple steps. I'm going to show you how you should install Python. First, start by going to the Python website. You'll see a download button. Let's see, download the latest version for your platform should show up automatically, I believe. But if it doesn't, go ahead and just select one of these links down here. Hit the download button. It downloads an installer. Run the installer. Now, in this case, I already have Python, so I'm getting this special installer. But if you did not already have Python, then you would see, hold on, let me just uninstall it real quick so that you guys can see. If you did not already have Python, then you would see an installer with one crucial option. That's what I'm about to demonstrate here. And it's actually this add to path option. So one second while that thinks about it. This is your opportunity to catch up and go to the Python site. On the questions. Okay, I'm going to take a couple of these initial questions while that's setting up so that I can show you the most important checkbox, the secret step in Python installation. So Patrick Kavanaugh asks if Python 3.10 is okay for this workshop. The answer is yes, Patrick, that's perfect. And let me go ahead and, all right, let's take a look now at, here we go. So this is the installer that you will see when you go to install, all right? So here's the very, very, very important button. I did not check this the first time I installed Python, which was why I had trouble, which was why I Googled fancy Python installation guides, which was why it turned into a nightmare for me. This button down here, add Python 3.10 to path. You need to check that. So what that will do is that will allow you to use Python from your computer's command line. If you don't check that button, you won't be able to use it from the command line. And then you'll be really confused because everyone else can use it from the command line. So why can't I? Something must be wrong with my installation. Trust me, I know that's what happened to me. So after you check that button, go ahead and just hit install now. And it installs like a regular program. And that brings us to our next point, which is Python is a regular program. So when I first started learning Python, I didn't really understand what it was. So that was part of why it took me a long time to figure out how to even install it, was because I wasn't sure what I was installing. Python is a programming language, right? So it's a way to write code. Code's what runs on computers to make software. So clearly a programming language is not software, right? So you have to install it differently, right? That's what I thought. I was wrong. In the case of Python, it is an interpreted language, is what it's called. So you can use the word Python in 2 different senses, I suppose. There's Python as in the set of grammar rules that allows you to type text and have it be recognized as code. So that's the abstract sense. Python's a language. But there's also Python, the software, which runs Python code. So in this case, what we've just done is we've installed Python, the software, also known as the Python interpreter. And just like a real-life interpreter can interpret from one language into another language, an interpreter who speaks French and English can interpret. If you speak English and you don't speak French, you meet a guy who speaks French, the interpreter can interpret the French into English for you so that you understand. Python is the same thing, but for programming languages, the Python interpreter is. So Python as a programming language is not just automatically supported by computers. It has to be converted into code which computers can understand. That's why it's called an interpreted language. You write the Python code, and then it is converted into lower level code, which can run on a computer just natively. So you don't have to remember all the particulars of that. The important part to remember is just that when you run Python, you are running a piece of software, not some abstract sense of something else. You're running a piece of software, just like when you run your telescope control software or an image stacker, okay? And you'll see an in-person example of that in a minute. Before I get to that though, I'm going to go ahead and take a look at the questions and see, have we got any questions on this topic before we move on? Okay. Let's see. So we have a couple questions about the Python installation. I see we have one here from Robert Duke saying you couldn't find the option to add Python to path on a Mac. Unfortunately, Robert, I don't know anything really about using Macs. I've always used Windows, so I can't help you with that. We're about to move on to using Python from the command line. The reason why you would check that checkbox, add Python to path, is so that you have the ability to use Python from the command line. What I recommend is that if that option was not presented to you, go ahead and follow along with the next part and try to use Python from the command line. And if it works, great, don't worry about it. That means it was automatically set up for you. If it doesn't work, you're going to need to just look up on your own how to set it up on a Mac so that you can use it from the command line. Okay, next question here comes from Craig Babbage, who asks, what about running Python through Spider? Okay, so I don't know much about Spider, except for I believe it's a Python IDE, integrated development environment. So yeah, let's go ahead and talk about that real quick. So there are lots of different ways to run Python. I'm about to show you the ways that I recommend doing it. They're quite simple, but honestly, there's as many different methods out there as there are programmers, pretty much, because everyone's very particular about their setup. So one of the most popular ways, if you're not just running it with what I'm about to demonstrate to you, is to use an IDE, integrated development environment. And I actually do use an IDE myself. I will pull it up and show you. Here we go. This is called Visual Studio Code. I don't even remember why I chose this particular one. I was still in the stage of being very confused about what Python was, and I was following some guide and it said install Visual Studio Code, so I did. I like it because it highlights my different variables for me, and I think that's very nice. But honestly, I don't use many of its features, and I'm basically just using it as a text editor. So what I'm going to recommend to you is that when you're first starting out, stick with using Python just in a regular text editor. All these other options that you will find, like Jupyter, IPython, Spider, you can do custom setups like distributions like Anaconda. You're going to find guides written by people who strongly recommend that sort of thing. And that might be a nice, those might be nice little tweaks that you want to make once you're a lot more advanced. But when you're just starting out, you really, really, really genuinely don't need them. And they're harder to install. And in my opinion, if it's hard to install and there's no real benefit, there's no point in pulling it in when you're just a beginner. So that's a very long-winded answer to your question, Craig, about running Python through Spider. Basically, what I'm saying here is that there are lots of options for running Python. If you're running Python in a way which works, as in you run the code, you don't get errors, you're not having to deal with tech issues, that's good. Stick with that. If you're just starting, you haven't got any way that works yet, go with the simplest option, which I'm about to demonstrate. Don't bother with all this extra stuff that the internet guides are recommending. Okay. Let's see. Okay, we have a comment here referring to one of the previous questions. So this comment came from Sarah Beck at HQ. Hi, Sarah. Sarah says that she saw the same thing with Max, where there was no option to check add Python to path, but it still worked from the command line as long as she typed in Python 3 instead of Pi when she went to run Python. So that's good to know. Thank you, Sarah. Okay. Now I'm going to go ahead and move on to the next part of the presentation because I think that that will cover most of these next questions, which are here in the Q&A box. So we have now just installed Python. Now the question is, how do we tell whether it worked? And I'm about to show you how you can do that. So let me move my screen share here down towards the bottom. Can you guys see my taskbar? Hopefully you can. Okay, now this is how you do it on Windows. I'm not sure exactly how you open the terminal on Mac or Linux. If you're using Mac or Linux and you're not sure how, I'd say just Google it. But on Windows, if you want to open the terminal, you go down to the bottom left, click in the search bar, and you can type in CMD is what I usually type. That's CMD for command. You can also type in command prompt, or you can type in terminal. Whatever you type in, it's going to suggest up here the command prompt. Go ahead, click that, and that opens. Here we go. This is the command prompt, aka the terminal. Same difference, you know. I might mix up those terms. Sorry about that, but it means the same thing. All right, so let's go ahead and check and see if Python was installed. Now, I believe, let's get this out of the way real quick. I've been running Python 3.8.6, I believe, because that's what was current when I installed it. Python 3.10 is now out. It's very, 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 very similar. However, I think they made one change, which is that now you type Pi instead of the full Python. So I'm going to be typing Python throughout this webinar, but if that doesn't work for you, try typing just PY. So to check whether it's installed, I'm going to type Python -- version. And there we go. It prints out my Python version. Now you go ahead and try that in your terminal. If it does not print out a Python version and it instead says some error about, you know, Python was not recognized, that means the installation was not successful. So I'll give you a minute to go ahead and try that out. Okay, and I'm going to go ahead and just test out what Pi does. It may run Python 10 automatically since I just did. Yes, so I have two versions of Python installed now. I have the new version, which I just demonstrated installing, and the old version. I guess I'll go ahead and use the new version since that's what most of you will be running. The difference is very little. The actual code is written the same, you know, whichever you have installed. Okay, so now that we're here in the command line, let's go ahead and talk about some command line basics. So there's two main commands that you're going to need to know to use your terminal effectively if you've never used it before. There's the command which runs a program, which is literally just typing the program's name. And that's what we've just done. So in order to run Python, we just type in the name Python and hit enter. There we go. Now I'm running Python in interactive mode. I'm going to go ahead and close Python real quick because we're not quite ready for that. The other important command to know about is how to mount a directory. Basically, this is how you open a folder, but in the command line instead of using your Windows Explorer. So in order to do that, you just type cd and then the name of the folder. So I'm going to go ahead and move to my desktop. CD, let's see, how many times can I misspell desktop? CD desktop. There we go. There we go. So now the command prompt is located on my desktop. And there's not really a visual difference except for right here to the left of the cursor is where you'll see the current folder displayed. This might be important sometimes because when you're running Python, it will by default be looking in whichever folder the terminal is looking in. So right now, if I run Python, it's just started Python from the desktop, basically. If I tell it to go look for a file or to go load a file, it will look on the desktop first. If I want it to look somewhere else in the desktop, I need to give a path which is relative to the desktop. Or I can cd to the location where I want. So if I want to look in my user folder, I go up a level using that .. Okay, here I am. So those are the two commands that you need to know to use your terminal effectively: how to mount a directory and how to run a program. I'm going to go ahead and check the Q&A box and see if there's any questions here about the command prompt. Okay, so we have a question here from Albert Stewing, who says he installed Python starting with the search box in the lower left. Yes, that's a valid way to install Python, I believe. I've never done it that way, but if it works, good for you. Launching Python from the search or the command line launches with two different starts. Okay, so we are about to go ahead and go over some details of how exactly you run Python code, and hopefully that will clear up any confusion here. Okay. I'm just dismissing the questions which have already been answered. Oh, yes, and we had one question here about the AAVSO Introduction to Python link. I'm going to go ahead and put that in the chat so that those of you who joined late can access that. So there's the link. Okay. So let's go ahead and pull the terminal back up. Here it is. And in fact, let me zoom in a little bit for you guys because we're doing a Zoom screen share and I know how that is. So we're going to go ahead and test out Python in the terminal. This is method number one, the method number one that you can use to run Python code. So I'm going to go ahead and launch Python. And remember, you launch a program just by typing in its name. And there we go. Python, the interpreter, is now running. So it's a little bit different from regular software in that there's no window that pops up for us to click on and use. It's just waiting for us to type in some text so it can read it. But it's kind of an invisible program. So it's like software in every way, except for we don't have a visible window we're looking at. In this case, we're running it in the terminal. Terminal kind of becomes the visible window, so you can think about it like that. Whenever you see these three greater than symbols here, that means that it's waiting for you to type in some code to run. So let's go ahead and type in some Python code. How about the classical first program, the Hello World program? So this is kind of an old tradition in computer science, is that the first program anyone ever writes is one which prints out the words Hello World to the console. Python comes with a built-in function which will print out anything that you put in it. So we're going to type out this function, print, and then to use a function in Python, also known as call. So to call a function, you put parentheses after the name of the function, and then put whatever data you want the function to have inside those parentheses. So here I'm going to type in hello world. And then when we hit enter, this will run this single line of code. That's how interactive mode works. And the output will be shown below the line of code. So here I'm told it to print hello world, and it did that. It displayed hello world on the line just below. It's kind of a useless program, but it's a good start to see how functions work in Python. So let's go over a couple of the basic units that you have in Python. So I've just shown you a function, which is sort of like a mathematical function in that it takes an input and produces an output, although this output is not on a graph. Sometimes Python outputs are on a graph. We'll see that in a minute. Python also has the concept of variables, which are, once again, kind of similar to the way they are in the world of math. You can create a variable by typing in whatever name you want the variable to have. Let's say I want to store the name of my camera. I'm going to type in a name here, camera underscore name. It's traditional to use underscores in the place of a space in a variable name for Python. A variable name won't work if it has a space in it, so that's why we use underscores instead. And then I'm going to type in the name of my camera as a string. String means text in Python, and you create a string using these quotes here. So if a bit of text is in between quotes, it's automatically turned into a string, and you can store it that way. So here, let's say that that's my camera name. Now, if I hit enter, nothing happens because we didn't tell Python to output anything. We just told it to store that name. But now it is stored, and it will be stored for the rest of the session unless we intentionally go in and change it. So I can create several variables if I want. Let's go ahead and make another couple variables. I have no idea what the RA of Betelgeuse is, but we'll use we'll go ahead and put in a number here so that you can see how you create numerical variables. And you just type in numbers without quotes in order to make them be recognized as proper numbers and not text. And now if I want to see the value in a variable which has been previously created, I can type in just its name. That tells the interpreter to print out the value. So there we go, we see the value appear. If I want to do some math using a variable, I can do that. So like here, if for some reason I want to see what's the value of twice the RA, I can do RA times 2. It outputs that value. Whenever a value is output in Python, you can capture it into a new variable if you want. So twice RA equals RA times 2, and now that is stored there. So there's some of the basics of how you use variables in Python. Now, just manually specifying variables like this is not the most powerful way to go about things. You still have to do a lot of manual input to keep track of anything. Okay, hold on. I see that we had a comment come in that the window's still too small, so I'm going to zoom in a little bit more here. Let's see. Hopefully that's better for y'all. Sorry about it being too small. And then, okay. So that's variables. Now let's go over collections. So collections are one of the most valuable tools that you have here in Python. And that's a way to make a list of variables. So here, let's go ahead and make a list of the variables that we've created so far. So I'll just go ahead and say So a list is created using these brackets. Anything that you put inside the brackets will get stored inside that list. And then let's say that we also want to add to this list some stuff that's not existing variables. You can do that. So let's say that, I have the RA specified, but I don't have the deck yet. So we'll do type in some value that we'll know later is the deck, and then print it out. There you go. There's all your stuff stored together in a bundle. So that's called a collection. That sort of list is. There are other types of collections. One of them is a dictionary, and it's the other one that I want to introduce you to today, because a dictionary allows you to look up values by their name or their key value. So let's go ahead and just start over here, since that was getting a little bit messy there. And create a dictionary with, say, some information about our target, and say that we want to store the target's name. We want to store its minimum magnitude and its maximum magnitude. So the way that a dictionary works is that you put in the label for the value, and then a colon, and then a value. So here we're going to make the name be Betelgeuse, minimum magnitude, and oops, we don't want that to be, and then maximum magnitude here can be whatever. And there we go, that's a dictionary. So the useful part of this is that later on in your code, when you want to refer to a specific value for the dictionary, you can index it using these brackets, and then whatever parameter you want to find out, you put here inside the brackets, and it outputs that parameter. Okay, so I think that covers most of the basics about handling variables and data in Python that we're going to need in order to understand the examples I'm going to run through. So at this point, I'm going to speed up a little bit and start going through some examples of astronomy related things that you can do in Python. So one of the very most powerful parts of Python is that of packages. Packages are bundles of external code created by other people, created in a way that's very reusable, that you can install on your system so that whenever you want, you can pull in this code that was written by other people instead of having to constantly reinvent the wheel yourself. So I'm going to show you how to install a package. I saw that there was a question about that earlier down here. So we had a question come in about installing packages, also known as modules, saying that there was some trouble, and he was getting an error message when he was trying to install a module. I'll show you why that is. So if you are here with Python running and it's waiting for you to type in a line of code, right? So you have these 3 greater than signs down in the bottom left, it's waiting, and you type in pip, that's the Python package installation tool. You tell it to install, and then you type in the name of your package, and then you run it, and oh no, it's giving you an error. Why is it doing that? That's because Python cannot run pip, the Python installer, from within itself, right? So in order to make sure that your installations don't fail like this, make sure that you close Python, the software. So you can do that typing exit function here. And there we go. So now Python, the software, is closed, and we can run pip, which is its own software, tell it to install, and then type in the name of the package we want to install. We're going to use a couple different packages today. Here's one called Astropy. When you type in pip install Astropy, it runs and does a bunch of stuff automatically. In my case, I already had it installed, so it tells me that. Requirement already satisfied. But in your case, it'll run through some information that's just general status messages. And at the end, you shouldn't see any messages about failed to install. As long as you don't see a message saying failed to install, it installed fine. Congratulations. Okay. So let's go ahead and install a couple of different packages. So let's also install NumPy is one that we're going to make use of. Pip install NumPy. And in fact, you can install multiple packages at once if you want. You just type their names separated by a space. So you could do pip install Astropy, NumPy. Matplotlib is one that we're going to use today. Another one is Astroquery. So I'm going to leave that up here for just a minute. You guys go ahead and run this command down here, pip install Astropy, NumPy, Matplotlib, Astroquery. Those are 4 packages that we're going to use today. 4 of the most popular packages for astronomers. All right, I'm going to go ahead and wait just a minute here so that you have time to type. Okay, I see we had one comment come in here from someone who is having difficulties installing Matplotlib, and it looks like in that error message, Matplotlib may have been typoed. So it's spelled Matplotlib. There's only one L at the beginning of lib. So go ahead and try that again and see if you're still getting an issue. If you are, let me know. Okay. So you can do this for really pretty much any kind of package that you want to use. I'm going to go ahead and run this command now. I already have all of these installed, so it's going to tell me that, but there we go. All right. So now we're getting into the fun stuff. This is how you start using Python for astronomy. So let's go ahead and start by opening up a FITS image. How about that? For me, FITS images have always been a little bit of a pain, and it feels a little bit unnecessary for them to be such a pain because they're very much a standard format. Well, okay, there can be some differences from FITS file to FITS file, but we've been using them for decades, many decades, and it seems a little bit silly to me that the software that you need to use FITS files is still so persnickety. So one thing which I was really quite thrilled to find out about when I first started learning Astroquery is that it has a whole section just devoted to FITS file handling. So that if you need to make a particular edit to your header or change the format in some small way, this is a kind of a frequent thing if you're having to upload FITS spectra to AVSpec. I help people with that frequently. We have some very particular settings as far as FITS files go that you need to make sure that your headers have all these keywords in them. And if they don't have all those keywords, sometimes it's a pain to edit it. No longer with Astropy. So let's go ahead and run Python and import Astropy's FITS tools. So in order to use a package, it's not enough just to install it. You also need to import it. And that's what allows you to access it from your current session. Okay, it's like loading it. And I see a question here from Jerry Horn asking if you need to install it every time you run Python from the command line. No, you don't. Now that they're installed, they'll be on your system until you uninstall it. Now, if you upgrade Python, the new Python will need to have the packages reinstalled. But as long as you're using the same version of Python, the packages, they're going to be there every time you go to use them. So in order to pull a package into your script, you just type import and then the name of the package. So here I'm typing import Astropy. It thinks for just a second. Astropy is a pretty big package, so it takes a little bit of processing. And then it's imported and it's waiting for me to type in some code. Now, you can also import just parts of packages. And for some particular tools, that's actually the standard, is instead of importing the package as a whole, and then having to type out the full address of the feature you want to use. So in this case, we want to use astropy.fits.fits. So in other words, we want to use the fits function in the fits folder of Astropy. If you're going to be using it a lot, that might get to be kind of tiring to type and make sure you don't have any typos each time. So what we're going to do instead is import just the part we want, the fits function. We're going to do that by saying from astropy.fits. That tells it that we're looking in the fits folder of Astropy. Import fits. Oh, I guess I got that wrong. I guess it's in is it in astropy.io instead? Oh yeah, it is. All right, please forget the part where I told you it's in a folder called fits, because it's actually in a folder called io. So from astropy.io, import fits. Sorry about that. This is actually a really good opportunity to show you guys where I find out about functions and the folders that they're in and how I can import tools. So let's go ahead and take a look at that real quick. Here I'm pulling up my browser, and I'm going to go over here and look up the Astropy documentation. So all of the major Python packages come with these really great websites where they have tutorials on how to use the package and kind of structural maps. They often will have sort of maps of the structure of the package so you can see which functions are available and where. So the Astropy documentation is particularly good. So here I'm scrolling down and I'm looking at all the different features that it offers. So, it's got tools for making data tables and handling times and dates and astronomical coordinates and stuff. And then, down here, fits file handling. And right here is where it tells me where I can get that import from, astropy.io.fits. And then if I click there, it gives me a bunch of tutorials about Astropy fits files. So really nifty. My recommendation is read the documentation just about as often as you can stand it. I found documentation to be kind of intimidating at first when I was first learning Python. And in my opinion, that's a little bit of a flaw of the system. The documentation for very advanced features is mixed right in together with the documentation for not so advanced features. But just keep that in mind when you're poking around, and you should be fine. Whenever you have a specific task that you want to accomplish, go to your Google search bar, type in that task, and look up how to do in Python. So in this case, I found out about Astropy's fits reader by searching how to open a fits file in Python. It seems weirdly specific. It seems like you probably won't get any results, but what actually happens is that there's lots of these code packages out there where people wrote the hard code for you, and those will come up when you do a Google search. So that's how you find out about what sort of stuff is available. So going back to our terminal now, we've imported fits, and now let's go ahead and open up a fits image. So let's see. Over here on my desktop, I have got a fits image. The This was one from one of the AAVSO net telescopes. I'm going to go ahead and copy its name. It's got a long, unwieldy name. And all right, let's go ahead and open this FITS file. So I'll say FITS file equals fits.open. So we're calling the open function, or more properly, the open method, which is on the FITS object. So one quick word I should say here is that you're going to come across when you're reading documentation, when you're reading tutorials and stuff like that, you're going to come across the words function and method. Method is exactly the same thing as a function. The only difference is that a method is attached to an object. So this method wouldn't work if I just called open, because open what? What's the context, right? It doesn't know that I want to open a FITS file because I'm just calling open. Now, as a matter of fact, open is a function in regular Python, so it might do something, but it wouldn't do what you're expecting. So you want to make sure that whenever you're calling a method from one of these packages, make sure that you remember to put the name of the object first. So fits.open. And then in here, I'll go ahead and just paste in the name that I'd copied here of the FITS file. All right, let's go ahead and hit enter. Oh, and it's telling me file not found error, no such file. Well, what's up with that? So, do you remember back at the beginning when I was talking about the two main commands for the terminal? You had the command to run a program, and you have the command to go to a folder. So you're probably going to run into this error a lot when you're first using Python, this file not found error. Don't panic when you see it. What that means is that Python, assuming that you typed the name of your file incorrectly, so check that, make sure that you did get the name right. If you did get the name right and Python still can't find it, what that means is very likely that Python is looking in the wrong folder. So let's try closing Python and looking at what folder we're in. And oh yeah, I'm in the folder c/user/Lauren, but my FITS file is on my desktop. So I'm going to go to the desktop. There we go. Now I'm going to run Python again, import my FITS tool, and then open my FITS file. By the way, if you are following along on your own terminal, feel free to open any FITS file that you have handy. I know that you don't have this particular FITS file from AAVSO net, but it doesn't matter. We're not going to be looking at, it doesn't matter which FITS file it is. We're just doing a general example. So, whoops. This is what I get when I'm talking while coding. What I meant to do was FITS file equals fits.open. There we go. Okay, so now we have a FITS file, and it's been stored inside a variable, which we have creatively named FITS file. But we're not seeing any pop-ups here, right? There's no window that appeared to just show us a GUI with the FITS file where we can edit it. So very typical for Python, we're going to do all of our changes here in the code. So the way that Astropy FITS files work is that you, when you open a file, it hands you back an object called an HDU list. Basically, FITS files can be looked at as a collection of headers and data, right? You have a header, you have a data set. If you have a really fancy FITS file, like it's from some of the professional observatories that store their calibration frames in the same FITS file, then you might have a header, main header, main data, calibration header, calibration data. So you might have multiple data sets in the same FITS file. In order to accommodate the fact that you might have multiple datasets. Astropy, it loads these headers and data, and then it combines each one into what it calls a header data unit, or HDU. And then it goes through the file, finds all the HDUs, and it combines those all together into an HDU list. The HDU list is what we've just gotten and stored in fits file, the variable. So let's go ahead and just take a look at that. If I type in the name of the variable to see what's inside of it, it shows me that there's a list. We know it's a list because it's indicated with those square brackets around it. That always means list when you see that in Python. Almost always. I guess technically indexing also uses that, but for right now we'll simplify and say that that means list. And then it's got all this junk in the middle. It has some information about like the memory address it's at. Don't worry about that. You don't need to care about that like ever. But the first part here where it says astropy.io.fits.hdu.image.primary HDU object, just skim that if it looks like what you're wanting, which is an object which was added by Astropy and it's related to fits and it's an HDU, so we know it's got header data because HDU means header data unit. Okay, this looks correct. We loaded a fits file. So in order to take a look at the contents of the fits file, let's go ahead and pull out this HDU object. So let's say HDU equals fits file, and I'm going to pull the first entry out from the list. Now, Python starts counting at 0. That's one of the most confusing things when you first start using Python if you've never used a programming language before. But it's very common for programming languages to start counting at 0. And the reason they do it is because when you start programming some more complicated functions, it actually does make things simpler, I promise. But at first, it takes some getting used to. But we're going to tell it that we want the very first object, so object number 0. And you can get an object out of a list by giving it this number. That's called indexing. There's information on all of this in the Introduction to Python guide. So you can review that at the link I sent out. So there we go. We've extracted the header data unit. Now let's go ahead and take a look at the header itself. So we can do that by typing in hdu.header. And this is checking the header variable, which is attached to the header data unit. So that's also known as an attribute. In the same way that methods are just functions, but attached to something else, an attribute is just a variable, but attached to something else. So here we're looking at the header attribute, right? So I'm going to go ahead and hit enter, and whoa, it printed out all this stuff. If I scroll up, you can see here's all the information in the header, right? So Astropy headers work like dictionaries. That's why I showed you guys the dictionary earlier. So if I want to get a specific value, I can go to the header variable here and I can index it. So I can tell it I want to get a value out of it and then put in the name of whatever value I want to get. So like, let's say I want to find out what the target is. I can look at the standard object keyword in the fits header. And oh, it tells me the target was SC1114, which is not a star I'm familiar with, but I could look that up in VSX if I'm curious. All right, so that's how you take a look at a Astropy fits header. You can edit a header in the same way. So let's say that I wanted to edit the telescope. Now, if you are familiar with fits files, you probably know that the cards here are usually capped at 8 characters. So that's why I didn't put an E here, because the telescope keyword is truncated. It's just telescope. So I'll go ahead and change this header here to, well, I happen to know that it's I think an epsilon 180 telescope. I hope I'm right about that. So now if we check that value, whoops. Notice that the first time when I access the telescope variable, I set it to be equal to epsilon 180 using that equal sign. So I told Python telescope equals epsilon 180. Now I'm just typing in the name because I just want Python to show me what it has stored. And okay, it shows me that the header was edited. So if I go ahead and if I want to go ahead and save this file, I can. I can do that with fitsfile dot. I don't remember if it's fitsfile.write or fitsfile.save. Well, why don't we pull up the documentation and take a look? So here we're back at the Astropy documentation. And then going back here, we'll go to, let's see, fits.open, and then I'm just scrolling through down here for an example. So I'm skimming through, this is a tip for reading documentation. You can skim through the code examples here and look for something that looks like what you're trying to accomplish. Image data, table data, creating a new fits. That's getting closer. So we're talking about, here we go. Write to. Okay, so this looks like a function that would be useful to us, hdu.write_to. I probably could have found that any number of ways with the search bar, but so we'll use this write_to function, and we'll call it just test.fits. And now, just on my desktop has just appeared the test.fits file, which has our changes made to it. So that's basic fits file handling. Now, so far it's been a little bit boring just messing with fits headers and all of that. Let's take a look at the actual data in this image. So we can do that by going back to the HDU. Remember, it's a header data unit. Let's take a look at the data. Ooh, that's a little bit messy. Well, that's because it's a fits image. There's like a billion pixels in here, and it's showing us a preview of just a few of the pixels. But this isn't really useful for interpretation, just having the pixel numbers here. So now I'm going to introduce you to one of the other favorite packages of astronomers, and that is the package called Matplotlib. So Matplotlib is all about creating graphs. It can make figures for publication. It can make scatter plots. It's good for displaying light curves. Really, whatever you want to plot, you can do that using Matplotlib. So let's go ahead and import Matplotlib. And the standard way to import Matplotlib, if you're just wanting to do some quick plotting and you don't need access to a whole bunch of super advanced settings, this is the way I recommend doing it. Instead of just importing Matplotlib like this, add on to your import statement, import matplotlib.pyplot as PLT. And what this is going to let us do is it's going to let us use Matplotlib's simplified pyplot mode using the shorthand nickname PLT. So it just makes the coding a lot easier later on. You'll see in a second. So I'm going to go ahead and import Matplotlib. The way that you show an image in pyplot is you just type PLT for pyplot, imshow, the name of the function we want to use. And then you have to give imshow the image that you want it to display. So let's give it hdu.data. All right, now it hasn't actually displayed the image yet. And this is one of the things that you want to keep in mind anytime you're working with Matplotlib. It's one of its quirks. It's designed to allow you to build up a graph one data set at a time. So you can plot lots of data sets on the same graph. And it doesn't want to get in your way by popping up a window every single time you add a data set. So when you want it to finally show you a window with your data in it, you have to tell it that by using the command plt.show. All right, so I'm gonna do that, and then here we go. Finally, some sort of a GUI window. So here we have a image displayed here in Matplotlib. We can see it's got some stars in it. Generally, though, it looks like most stuff in here is clipped to black. If you're at all experienced with astrophotography, I know what you're thinking, and that would be this image needs a stretch. So why don't we give it a stretch? To do that, I'm going to introduce you to another popular package that astronomers like to use, and that's NumPy. The standard way to import NumPy is to say import NumPy as NP. And these standard imports here, you'll see them in use when you're reading the documentation for the package. Just make sure that whenever you're reading about how to do something, you're reading in the documentation and following a tutorial, just import the package the way that they show, and that's generally a safe bet for whenever you write your own code too. So there we go. I've imported NumPy, and I'm going to find out what is the average value of the image. So let's say average value equals np.mean. So here I'm using NumPy's mean or numerical average function. And I'll give it the image data to work with. Okay, so it's just stored the average value in the average value variable. And now we're going to go back to our image and stretch it. Now there's a couple different ways you could do that. I'm going to show you what I think is the simplest way. Matplotlib actually has options built in for all sorts of plot configuration. One of those options is that you can set the black point and the white point. Now, Matplotlib doesn't call them the black point and the white point. It calls them vmin and vmax. But we're going to go ahead and just stretch the image using that black point and white point. And let's say that we want the black point to be just slightly lower than the average value, right? Because the average value statistically is probably going to be close to the sky level, right? So we'll say that's the black point. And then we want the white point to be just slightly over the average value because we're just wanting to take a look at the data. It's okay if we clip the stars. Okay. Now let's plot the image again, but this time we'll include the keywords for the minimum and the maximum. So here I'm giving it the data. All right, so now we have a recreation of what we did before, but we're going to add in some extra config options. These are called function arguments, more technically. So plt.imshow here, like many functions, it can take some additional configuration options, and you can find out what those options are by looking it up on the project's website. So in this case, I would go to the documentation for Matplotlib and look up imshow and then look at all the options I have, and it would be described there. In this case, I already know, because I use it a lot, that I can type in the options vmin, and I can tell it what I want the black point to be, and vmax, I can tell it what I want the white point to be. So I'll go ahead and plot that and show, and oh, there we go. That's much better. There's our fits image. So I'm going to go ahead and zoom in here. You can do that with Matplotlib graphs. They are pretty interactive. You can pan around if you want. So this is an example of how you use NumPy and Matplotlib in order to display an image. Of course, I cherry-picked these examples just to introduce you guys to a couple of the most popular packages for doing astronomy, but there's really no limit to the sort of stuff that you can do to your data using Astropy. So, or using Python. I suppose it's sort of accurate that I said using Astropy, because much of the magic does come from Astropy, but it's Python's really a sandbox for you to do whatever you want. You'll be shocked when the first time you start scrolling through the documentation for one of these major packages and see just how many options there are. Okay, and then I'm going to go ahead and show just a couple extra options, speed up a little bit here, and just maybe save this graph, give it a title, you know, do some sort of extra configuration. So let's go ahead, and here I'm pressing the up arrow button to bring up my previous command so I don't have to retype it. So there we go. I've brought up my previous command. I'm going to add another couple of options like CMAP equals grays. So that's one I use a lot. What this lets me do is change the color map. That's what CMAP means, color map, to grayscale, because the default Matplotlib, I mean, it looks kind of weird having an astronomical image in that purple and green and yellow thing. So I'll do that. Whoops. Okay, so it just gave me an error message saying that I must have misspelled grays. Yes, it wants me to capitalize it. Well, of course it does. These sort of errors when you're writing Python code, don't feel bad when you get an error. It really is much more common to write a line of code and have a mistake in it than it is to write a line of code correct the first time. Trust me on this. Writing Python is really like a continuous solving of little puzzles that get brought up. You know, you write the code that you think will do what you want to do, and then it will show you an error message. And then usually the information's right there in the error message about what you need to do in order to fix the error message, but it might take a little bit of decoding sometimes, and that's where the adventure comes in. If you're ever having trouble decoding an error message, pro tip, put that error message, just copy paste it into Google. I can almost guarantee you that someone else has had the exact error before. And make sure you read critically, you know, the sort of solutions that you're seeing, and try and figure out if that applies to your situation. Chances are it will. All right, so there, I've plotted it this time in gray. I'm going to add a title. Here, why don't we title it with the name of the target? So HDU.header object. All right, and let's also turn off, so Matplotlib graphs by default, you know, they have the X and the Y axis labeled with numbers, but we don't really need that when we're viewing an image. We don't care about what the pixel number is. So I'm going to go ahead and turn off that. I can do that using plt.axis, and then I pass it the config option off. So plt.axis off, and now if I go ahead and do plt.savefig, this is what lets me save my image in case I am wanting to do that. So plt.savefig as, well, let's see, what was the name? SC114.png. There we go. And now on my desktop appears this image. And there we go. It's our image. It's a little bit tiny though. If you run into that issue, all you have to do to fix that is actually just to pass in the DPI config option. So let's try that. And then, oh, look, much bigger now. So there we go. All right. That's just kind of an example of how you would putter around in Matplotlib and change some configuration options and explore a FITS file while you're at it. Now, of course, you can do much more than just view and edit the metadata of FITS files. I happen to know that there is a tutorial on the, well, I don't remember which specific forum. It's one of the AAVSO forums on our website. I remember that someone has created a nice tutorial for doing photometry with Python, actually completely replacing a software like vphot or something of the like, because believe it or not, there are packages for doing photometry, for identifying stars in an image and producing image cutouts and doing all the pixel math that you need in order to do that. I wouldn't recommend that you switch over to that as your first project because it's a little bit complicated in order to make sure that you are actually getting a correct result with high precision, but it's an option. You can do all sorts of image analysis with Python. Okay, so we've just taken a look at how you would load a FITS image. What I've just done was using an example of a simple 2D FITS image file, but this also works for other kinds of FITS files. Like if you have a 1D spectrum or a 3D spectral cube or something like that, then you can also load those files. Astropy is not limited in that way. So at this point, I'm going to go ahead and break for questions. I have another example, which I'm going to show in a little bit, but I want to give you guys some time to absorb that, mess around in your terminals, play with Matplotlib and Astropy's FITS image loading a little bit if you'd like to do that. And if you've been having any difficulty following along so far, now is a good time to ask some questions, and I can go back over stuff if you'd like. Okay, just looking at the questions which have come in so far. I see that we had one question earlier where the questioner solved it, but I'm going to go ahead and verbalize the answer for everyone else. So when you call plt.show in order to show your image, if you then go back to the terminal and start trying to write code, nothing comes out. It's like, wait, is my terminal frozen? What's actually happening there is that this Matplotlib image window is blocking the terminal. So until you close the Matplotlib image window here, no more code will be able to run because the code for this interactive viewer here is currently running. Oh, that's my keyboard smashing when I was trying to demonstrate that nothing would type. Okay. And then we also had a question here come in about FITS file headers. Okay, that's a good question. How standardized are the headers? Is there much variability in the header parameters? Very good question. So let's go ahead and take a look at our header here. And in fact, I'm going to go ahead and demonstrate in a loop how you would do this. So this is a feature of Python which I haven't shown yet, but if you have a list or a collection of any kind, you can loop over it. In other words, you can run a piece of code over and over, running it once for each of the items in the list. And that can be very powerful if you have, for example, if you have a whole set of images, maybe 100 images that you want to stack together. You don't have to write the same code out 100 times to load it. Instead, you can call a search that pulls up all the image file names in your folder and then loops over them. So you write the code once and the loop runs the code one time for each image. It's very powerful that way. Here we're going to use it to take a peek in the header in a way that is a little bit easier to view for me than the standard. You know, if you type hdu.header, you get this output that has lots of white space in it, and it's all spaced out and a little hard to read for me. So to demonstrate a loop, we're going to go ahead and say for, let's say, key and value in, so headers are like dictionaries, remember, which means that every value also has a label. So when you loop over them, you're going to get two values back. The value, in this case, the actual value of the fits header card, and the key is what they call the label on the value. So when you write a for loop, make sure that you account for that and that you make sure that you're looping over both the labels and the values. So here I'm going over the key and the value. And then I'm going to tell it to print the label and then print the, whoops. And here, let's print an equal sign so that it's clear what we're talking about, and then print the value. So now it's going to go down the fits header. For each line in the fits header, it's going to pull out the key, which is the label on the value, and the actual value, and it's going to print it out. And there we go. That's a more typical view of a fits header, what you might expect. So talking about the standard header parameters, all of this stuff down here towards the bottom, this stuff is not at all standard. So this is stuff which was produced by the AAVSO image pipeline. It might be useful for some people, but it's not what you would include in just your average header unless you had a good reason to. But then up at the top is where you usually find stuff like the more standard fits header values. So here we have these CR val and CR pics. Those will be automatically added by basically any camera capture software that you use, and they just tell software like Astropy how it's supposed to load the data. And then you have the relatively standardized values, like things like the longitude and latitude of your observatory, the air mass, the object name. Those are not, as far as I know, those are not officially standardized by the FITS standard. You know, you're not required to have them in your FITS files, but there's kind of a general agreement. You know, it's perhaps tradition is closer to the correct word to use. And so there's conventions about what kind of label you put on what kind of values. So object, you know, you would relatively rarely see, at least in the context of AAVSO databases, you'd relatively rarely see something like target equals SC114. It's always going to say object. And then here's some up at the top are more of the standard ones. So it's a mix. To the person who asked about how standardized are the headers, it's a mix. Astropy can handle all of it. I mean, it's a very flexible framework. Okay, so I see we had a couple more questions coming in about FITS files. So first question, this one comes from Ray Tomlin. Hi, Ray. Ray says, how do I handle a .fit file rather than a .fts file? Excellent question. The answer is you don't have to do anything different. As long as the actual content of the file is a FITS file, it doesn't matter what it's named. It could even be named, you know, abc.png. It doesn't have to be named as a FITS file. Astropy is going to look at the actual contents of the file when it's loading it. So. Okay. Then we had a question here from Richard Berry. How much memory is available for opening a FITS image? Suppose you want to average multiple 60 megapixel images. What will Python do? That's a very good question. My experience is that Python will use as much memory as is available on your machine if you force it to. You will get an error and run out of memory if you try to use more memory than is currently available on your machine. However, you might enter a period of extreme lagginess before that point. I speak from experience when I have tried to load data sets that were way too large before. If you try to load all of it into memory at once, you will get lag. With modern computers, I don't think that really happens with reasonable usage. However, what you're talking about with averaging together multiple 60 megapixel images, I guess I don't know. So there are methods. I know that there are methods for handling memory in Python for loading, only parts of images, and then averaging those parts together and then moving on to the next set of parts and averaging those. And that way you never have the entire set loaded into memory at one time. So that's one workaround. But personally, I don't have experience with that. So all I can really do is tell you about that and hope that's a lead for when you're doing your research. I can say that outside of that one time that I was loading these ridiculously huge model sets, and I was trying to do Monte Carlo simulations on a very large scale, and I ran out of memory then. That's the only time in years of using Python that memory's ever been a concern. Most things are relatively low consumption. Okay. So we have a question here from Rick March, who says, I noticed that distortion parameters are included in the FITS file header. Is there a way to plot the distortion across the image? So Rick, I've never done that myself, so I can't give you a 100% definitive answer. However, I can give you a place to start. So first of all, the information's there. So if you happen to know how those distortion parameters are applied, you can totally plot that just like a graph. There's also over here in Astropy, let's go back to the Astropy main page. There's this module here called astropy.wcs, World Coordinate System. And again, I've never used this myself, but I believe it involves, or it includes a lot of functions that are useful for that sort of thing, plotting distortion across the field of view in different coordinate systems and applying corrections for distortion. So that's at least one place that you can start looking, is the astropy.wcs module. Okay. And then we had a question here from Timothy Weaver asking, what file is the image placed into by Matplotlib? Okay, so that's a good question. So in this case, when I saved a file, I'll go ahead and save it again just as a demonstration because I think it's, well, it may not still be in memory. Here, I'll plot the image again. So I'm hitting the up button in order to go back through my history. Okay, here we go. So plt.imshow, let's say I call that plots an image. And then I do plt.savefig in order to save it. Now I get to choose where it will save this image. I can put in a different folder if I want. I would have to specify it in the file name, or I can just put in a regular file name. And then I get to pick the file name, and that's where Matplotlib will write it. So there's no specified output. There's no predetermined output. You get total control over that. So here, I'll just go ahead and save it as something patently false. Let's call it Betelgeuse. And in fact, it doesn't even have to have an extension on it. So let's show that. I'm going to just go ahead and save it as is. And now I have this file here called Betelgeuse, and Matplotlib automatically determined that it should be a PNG file, added the PNG extension, and saved it. And here it is. Now I'm going to delete it so I don't mislead myself that that's Betelgeuse later. Okay. Now, I see we had one more question that I want to address before we move on to our next example. And that was a question about the use of the different kinds of brackets. So we have parentheses, of course. We have square brackets here, and we have curly braces. And they all mean different things in Python. In fact, I believe that this one will be easier to explain actually after I start my next example, because we're going to switch over now from the command prompt to a text editor. So everything that I just did here in the command prompt was very simple. I was only writing 1 or 2 lines of code at a time. And that's the ideal time to use the command prompt, is if you don't need your code to be saved, if you just need to do some real quick modifications, you're not really going to have to repeat it in the future. You just want to write down some code real quick. Command prompt, great for that. Terminal, great for that. But what if you want to write a longer program? That would get really unwieldy writing all of it here into the command line. You would probably make a typo at some point, and then you can't really go back to the top and edit it. It would just give you an error, and then you'd have to start over, and that would be a huge pain. So the other main way to write Python code is using a text editor. Let's go ahead now and pull up a text editor. So I'm going to use Notepad++. Oops, that's my test there. Okay, so here's Notepad++. This is what I would recommend that you start out with. Like I was talking about at the beginning, there are lots of different options for where you can write Python code. Like I said, I write Python code in Visual Studio Code. I do that because that's what I got started using, so now I'm used to it. But honestly, I think that a better way to start out would be with Notepad++. So that's what I'm recommending to you guys. It's very simple. This is just a text editor like you're used to. I wouldn't recommend using something like Microsoft Word, because you want to be able to save as plain text, and formatting would get in the way, and it wouldn't highlight your variables and stuff like that. Notepad++ will highlight your variables, which is a very nice touch. So in order to write some code in Notepad++, hold on one second. I'm going to mute myself real quick. I'm still a little bit sick from earlier this week, so. There, sorry about that. You could just tell that my voice was getting a little bit nasally. Okay, so here in Notepad++, if you want to write down your code, you can write down as many lines in a row as you want. So here's an example using our program that we wrote earlier. So let's say, hold on. If I want to get the highlighting, let me go ahead and, all right, I'm going to show you, starting over, this is the correct way to start a new Python script. Make a text document to store your Python script in, and name it whatever you want. So let's say, I'm just going to call this one webinar script .py. If you edit it in the .py file extension, then that's what tells Notepad++ that when you're editing it, it's supposed to highlight your words to help you write better Python code. So here, let's say from astropy.io import fits. And now when you hit the enter key, it's not going to run the code immediately because you're still just here editing the text file. What you'll want to do is, here I'm just recreating what we did earlier. Put that in quotes so that it loads correctly. HDU equals. And then one of the common conventions about Python that I wanted to share with you guys is that when you're writing a script file like this, it just makes things a little bit neater if you put all of your imports up at the top, so that all of the code below that point can access your imports. So I'm going to go ahead and put up here. And then okay, so here is a simple version of the script that we were just doing in the terminal, but I've just written it down in a text file. So I'm going to go ahead and save it. Go to File, Save, or you can press Control S, right? And now that I've saved this file, if I go back over to the command line and I type in Python, but I don't hit enter just yet. I don't start Python to software. I just get it ready. I type in the name and then I hit space. And then I type in the name of the text file where I've just written down all of my Python code. And now I hit enter. What that tells it is that the Python interpreter should launch and then automatically run all of the code which is in the text file. So here, if I do that, there we go. It just automatically ran through all that code that we did earlier because it was written down in the text file. And the advantage of doing it this way is that now I can go back and I can edit the code. I don't have to write it all from the beginning every time that I want to plot this again. I can save it. I can run it next Tuesday if I want. And I can write some more complicated stuff now that I see all of this laid out right in front of me. Let's see, I see someone asked if I could share the text file with you guys. Okay. Just one moment. As a matter of fact, I will go ahead and just copy paste this code into Zoom right now so that you guys can run it real quick in your own text editors, paste it into a text editor, save it, and then run it with Python as a test. Here we go. So feel free to just copy that over. Later on down the line, just so you know, I will be sharing a couple of example scripts that go over the same stuff that we've just gone over in this webinar today. So you'll have that to refer back to. And of course, you'll also have the Python guide, which I'll go ahead and share again for those of you who arrived late. Here's the link to that Python guide, which I wrote. And this covers all the same stuff about Python. It doesn't cover Astropy, but the other scripts, which I'll be sharing soon, do cover Astropy. Okay, so this is the other way that you can run Python code. Write it into a text file, save the text file, and then run the text file here by telling the Python interpreter that you want it to run everything in that text file. So now we're going to use that to make a bit more complicated script. So what if instead of a text file, you wanted to display, let's say, a light curve? How about we go to the AAVSO website and pick ourselves out a light curve. So here I am on the AAVSO website. I'm going to go down here to submit and access data. Click on that, and then click on the download photometry form. Okay, and we're going to get ourselves an AAVSO standard light curve data file. Let's do Betelgeuse. And then I probably don't want all of the Betelgeuse observations ever done. So I guess I should put in, let's put in a date early enough to see the great dimming. How about that? So we'll do from January 1st, 2018 to January 1st, 2022. I'll be a nice person and fill out my information here. I guess I'm an educator today. And I'm planning on using this for education and outreach, go figure. And then I'll get my data file. All right, so you go ahead and download a light curve. If you've been following along, go ahead and download a light curve from the aavso.org/data download page. Let me go ahead and put that link in the chat. And I'll give you a minute to do that and take some questions while we're waiting. Okay. So let's see. Ah, yes. Okay, going back to the use of the different brackets. I said I would do that after we loaded into Notepad++ here. So I'll do that. So basically, you have three kinds of brackets. You have the parentheses, you have the square brackets, and you have curly braces. Parentheses are used to call functions. So basically, they're a way of telling a function, here's the data I want you to use. So up here, you can see that we use them to tell the fits.open function that I want you to open this file. We put the file we wanted to open inside the parentheses, and then it knew. Down here, when we called imshow, we told it that we wanted to show an image, and then we put the image that we wanted it to show inside of the parentheses. Some functions don't need to be told anything. Like this plt.show function, just calling the function is enough because that's all that function does is it makes the window pop up. Passing in any data, giving it data wouldn't matter. The data was already given to it with imshow, right? So there's no need to give it more data. So we called the function anyway because this the parentheses are what tell the function, okay, it's time to run. But we didn't need to give it any extra data. So these ones we left empty. So that's basically what parentheses do. They tell a function it's time to run, and optionally, here's your data from when you're running. Here are the square brackets. So square brackets are used to make a list. So you can create a list just by typing those square brackets. And then if you want, you can put data in the list. You don't have to put data in the list, though. You can just create an empty list if you want. Square brackets are also used for getting data out of collections. So like here with our fits file, we wanted to get the first item out of it. And remember, Python starts counting at 0. So we told it, square bracket, that means get ready to get something out of your collection. Get the first item and square bracket. That's called indexing. So I have some more information about indexing in our Introduction to Python guide, which the link's been put in the chat a couple of times. Feel free to consult that. Okay. And then for the curly braces here, curly braces, the main use is to create dictionaries. So whenever you want to create a dictionary, you would put curly braces, and then the data for the dictionary goes inside the curly braces. So That's an example of a dictionary. You have your labels, which are highlighted in orange here in the Notepad++. And then you have your data, which is attached to the labels by this colon. And what makes it a dictionary is these brackets around it, these curly braces. So that's what curly braces are used for. So I hope that answered that question about explaining what all the different types of braces can be used for. Okay, so going back to our current project at hand, giving you guys some time to go download a light curve. I noticed that we did have one question about that. So someone had asked, what should we choose for the options about, do you want discrepant data included? And do you want diff and step data included? What format do you want? So what I would recommend choosing is, no, I don't want discrepant data. No, I don't want diff and step data. And give me a regular CSV file. So let's go back at the form. Here's what I have chosen. No discrepant data, no diff and step data, and then I want a CSV file. You can use files generated with the other options. That's just what I would recommend for general use, because you probably don't want the discrepant data in your data set. That would be data that was judged to be outliers. You know, maybe the weather was really bad one night, and so the photometry came out bad or something like that. And so it's automatically excluded unless you specifically say, I want to see outliers too. And then the diff and step data is just some additional data that you're not going to want to be plotting probably. So I always say no. And then in what format should the data be returned? Comma delimited. This is not just a Python thing. Comma delimited is the most common data format. Even for when you're loading your light curve in other software, it's generally a safe bet that you want to use commas instead of tabs or spaces. So I hope that answers that question. And then I see we had one more question come in about what you do at the command prompt in order to get Python to load a text file. So just as a reminder, here's what you do. You type in Python, or depending on your Python version, you might just type py. If you're running the most recent version of Python, I believe you just type py. So if you're hitting issues, that might be why. And then type in the name of your text file. And ignore that error. That's just because I haven't installed Astropy for Python 3.10 yet. But for you, you have just installed Astropy, so you shouldn't have that error. Okay. So moving on to our example. We have a light curve. We have downloaded it. I guess I need to pull it up from my downloads folder. Here's my light curve. So here I'm going to just name it very creatively, lightcurve.csv. I guess I should put the name of the target in there. So let's say Betelgeuse lightcurve.csv. Okay, so go ahead and rename your CSV file to something easy to remember if you'd like. You can use the random numbers name that it was given, but if you do that, just make sure that you copy paste so you don't make a typo. Now, all of this stuff here from our previous script, I'm going to go ahead and just delete because we're not doing that anymore. And I'm going to set up for loading our file. It's not a fits file, so I don't really want to use the Astropy fits loader. That wouldn't work. What I want to use this time around, as it turns out, Astropy has a general data loader, which works for all kinds of data formats. And it's called table, the table reader. So I'm going to go ahead and say from astropy.table import table. Notice that the second table is capitalized. That's important. First table not capitalized, second table is capitalized. And you know what? I'm going to increase my font size real quick so that you guys can see this better. I think here's where I go for that. There we go. All right. So from astropy.table, import table. And then this is the way that you open any non-fits data when you want to load it into Python. And you just type table.read, and then you put in the file name. So in this case, I named my file betelgeuselightcurve.csv. So I'll type that in. All right. And then here's a tip. You might sometimes get an error when you're reading standard AAVSO files, unless you add in an extra configuration parameter here. So as it turns out, it's possible for AAVSO observers to have special characters in their names. Now, Astropy doesn't always know whether it should expect to have special characters in files. So what I recommend doing is that when you're reading AAVSO data, just throw in a little extra parameter here, which says encoding equals UTF-8. So UTF-8 is the encoding that AAVSO data files use. And just by throwing that in, you're being on the safe side and making sure that when Astropy goes to read the table, it won't create any errors if it sees special characters. So there we go. I've just made the line that will read in our data. And then let's go ahead and just take a look at the available column names. So I'm going to do that by typing print data.callnames. So call names is a variable which is going to be available on any table object. You know, as soon as you read a table in with Astropy, you get a table object. So data is now a table which has your data in it. And if you want to find out what sort of columns are available, you look at the call names attribute. So I'm going to save this script. I'm going to go over to my command line here. I'm going to type in Python and then the name of my script, and then hit enter. And there we go. It's showing me all of the different column names that I can choose from. So in this case, with the AAVSO standard light curve format, I see that I have one column here that's called JD. Okay, that would be the date, Julian date. And then I see I have a column called magnitude. So that's the magnitude measurement. It's also labeled with the observer code, the filter, lots of that sort of good stuff. But for right now, we're just going to look at the JD and the magnitude because that's what we need in order to plot the data. We're going to put JD on the x-axis and magnitude on the y-axis. So let's go ahead and do that. But we're going to need to import Matplotlib to do that. So here I'm using the plt.scatter function instead of imshow because this data isn't an image. It will be better to plot it as a series of scatter points. So I'm using plt.scatter here. And then what scatter expects, and you can tell this if you go to the Matplotlib documentation, what scatter expects is for you to give it two variables. The first variable represents the x-axis of your graph, and the second variable represents the y-axis. So here I want for the Julian date, JD, to be on the x-axis, and I want for the magnitude to be on the y-axis. And then let's not forget to show, and I'll clean up this print statement because we don't need that. Okay, now I'm going to save my script. This is what it looks like. I'm going to go over here to the command prompt and run my script again. Python script name, enter. And then here we go. Oh no, why does our light curve look like that? That's really messed up. So this is going to be a common issue that you will run into with data sets. And I wanted to go ahead and demonstrate it for you guys so that you know what to do, because it's a little bit of a weird issue to troubleshoot. Like, what's gone wrong with the y-axis here? That's just weird. So what has gone wrong with the y-axis here is that our magnitudes are being treated not as numbers, which are sortable, but they're being treated as text. So this is what a graph looks like in Matplotlib when you try to plot data that's actually text. So I'm going to show you how you correct that. So the reason that it's being treated as text is because it was going through the magnitudes and it was looking like, okay, yeah, that's a number, that's a number, that's a number. Oh, this one includes a less than sign. It's text. You can't have a less than sign in a number. And the reason why there are less than signs on some of these measurements is because it's possible to submit an observation to the AAVSO, which is a fainter than observation, right? So it means I looked for this star, but I couldn't see it, so it must be fainter than my limiting magnitude. So one of the first things I always do when I load a AAVSO light curve is I take out the fainter thans. And for that, here's one way that you can do that. I'm going to use a loop that looks at every one of the observations in this data table, checks whether it's a fainter than or not. And then if it is a fainter than, it should mark it for deletion. So this is the habit I've developed over years of coding with Python, is that I make a variable called rows to remove. I make it a list, and it's empty at first. But then I look through data using a loop. So I say for observation in my data table, I say if the less than sign is in the magnitude, or whoops, I shouldn't have said data there. I should have said the observations magnitude. Then I add to the rows to the remove list the location of this observation, or its unique identifier. So I can get to that by saying observation.index. Whenever you're looping over an Astropy table, you can use this .index, and it will be unique for every row in that table. So that's a little trick you can use. And now that I have sorted out all of my rows to remove, I need to actually remove them from the table. That's very simple. I type the name of the table, .remove rows, and then I give it as data the list of all the rows that I want to remove. So it'll go look through for any of those rows and it'll pull them out of the table. So this right here is my code for removing fainter thans. Whoops, I missed a quote there. There we go. This is my code for removing fainter thans from a light curve. All right. So just to go over it one more time, I create a list. Then I start looking at each individual observation in the data table using a loop. If a fainter than sign is in the observation's magnitude, I record the location of the row in my rows to remove. And then at the end, I actually do remove those rows from the data. Okay. And one other thing is that it's possible that, or actually it's probable that when Astropy was reading this table in, it also saw that, hey, there's some text in this. It's not all numbers. And it went ahead and it just converted everything to text. If that's the case, which I'm pretty sure it is, I'm going to need to convert the numbers back to actual numbers instead of being stored as text. If you ever find yourself in that situation in Python, like in this kind of situation, you can do that by using the float function So float is a type of number, and if you put some data into it, like the observation's magnitude, it will convert that data to a float number. And then, of course, we need to store it. So I'm going to say convert the observation's magnitude to a float version of the magnitude. So going back over this, we have our list to keep track of what we should remove. We loop over the data. If it's a fainter than, we take it out entirely. If it's not a fainter than, we want to keep it, but we convert it to a number. And then we remove any of the fainter thans that we found. All right, so this code, you can see how this would have been a pain to write it all down in the terminal. But here in a script, it's not so bad, because we can go back, we can highlight stuff, we can edit stuff. When we wanted to import matplotlib.pyplot, we could go do it at the top, so it was out of our way. I'm going to go ahead and save this now. Go back to my terminal and run the script. And, oh, why am I getting the same issue here? All right, well, let's do a little bit of debugging together. Oh, I see. Okay, so a little bit of information about Astropy here. This has caught me out a number of times. So Astropy, the way that it keeps track of data is that it's just like an Excel spreadsheet. It's got rows and it's got columns. So each row of data here is one observation, and it can contain all sorts of types of data. But each column representing, in this case, the date or the magnitude, can only be one data type. So the column can either contain text or it can contain numbers, but it can't contain both. So if you try to put a number into a text column, it gets converted to text, so it can fit into the column. So that's what I did wrong here. I had it going through and converting the text to numbers, but then putting it right back into a column, which was set to the text mode. So what I'll do is I will take this and I will apply it after we've removed all of the text rows. And I'll set the whole column at once. I'll say the magnitude column should now be equal to, right now it's a list of text. What I want it to be is a list of numbers. So I'm going to use a list comprehension for this. Float of mag for each magnitude in data magnitude. Now this list comprehension thing was kind of scary to me the first time that I saw one, but it's really simple. It's basically a way to build a list without having to write it out on multiple lines. Like here, I'm building a list, writing it out on multiple lines. But here's a shorter way to do that. Sometimes it's easier, sometimes it's not. You just use whichever one you prefer. You're not missing out on anything if you don't use a list comprehension right away. But what it's saying is that for each magnitude inside the list of magnitudes, convert it to a number and then store it in a list because it's inside these list brackets. So that's just a shorthand way of converting all of these to numbers. And then here I have the original column, which I'm setting to be equal to this list of numbers. All right, now let's run it again. And this time it should work. There we go. All right. Now it looks a little bit unexpected because the default for Matplotlib is to plot larger numbers as higher, smaller numbers as lower. Of course, we do things backwards in astronomy with the magnitude system. But here is our light curve. We can zoom in on it if we want. Here we can see the great dimming. Looks like a great brightening with this scaling. We should probably fix that. One quick way to fix that, there's a function in Matplotlib just for that. So before you call your show, any time before, just go ahead and type plt.invert y-axis. Handy dandy function to do that. So if we add that to the script and run it again. Really? I forgot. Now, why isn't that working? I just used that on one of my scripts. All right, well, here. You guys get another troubleshooting demo. Matplotlib, invert y-axis. Here's a very useful site. This is kind of how I taught myself programming, Stack Overflow here. When you search the way that you want to do something, this is a question and answer site where people ask questions like this and then get answered. And oh, here's the issue. I was supposed to call the function plt.gca.invert y-axis. Okay, so there we go. That's our answer. I'll come back over here and say plt.gca. Now what that's doing, I know because I have some experience with other Matplotlib stuff, it's looking at the graph you've already plotted and then getting the current axis and then inverting it. It's a little convoluted, I know, but that's what that is. And there we go. So Matplotlib comes with lots of different methods for customization. You can keep fine-tuning for, I guess, as long as you want. You can come up with publication quality graphs this way. Of course, this is just a quick plot to take a look at some data. But there you have it. That's how you load local data. Now, I think this is a good place to go ahead and stop for questions. Does anyone have questions about using tables or loops or anything like that we've just gone over? Okay. See that we had a couple of questions here, which are not related to, oh, I see. Someone would like to see the script again. Good point. Let's go back to, here's the Python script that we were just working on so that you guys can be seeing that. And in fact, I'll go ahead and copy paste this into the chat so that if you would like, you can go ahead and just paste it. Now remember that you'll need to change the name of the light curve to match whichever light curve you downloaded. But there you go, that's a script to, oops, I didn't copy the astropy.table thing. It wasn't quite scrolled enough. There you go. All right, so that gives you guys a starting point. And then I saw that we had a couple of questions here about the availability of materials after this webinar is done. So those were really good questions. Someone had asked if when will the presentation be available on the website? The answer to that is I'm not sure. I know that these recordings generally take a little bit for my coworker to prep. There's some manual editing that needs to be done. So it may be a couple weeks for that. However, that doesn't mean you won't be able to review the recording immediately, because there will be a recorded version of this available on Facebook immediately. That one doesn't have to be edited. So we have it set to automatically upload as soon as the webinar ends. So if you would like to come back and review this presentation, you can do that by going to our Facebook page, which is called AAVSO HQ. Let's see. Okay, we had a question related to loading the script and running it. Okay, so here I'm taking a look at the terminal. So we had someone say that they can't load the script even when they name the file with the exact name and put it on the desktop. So here are a couple things to check when you're troubleshooting. First of all, make sure that the folder that you have open in the terminal is the desktop. Let me close this window so that, there we go, that frees up my terminal. So right here, when it's waiting for me to type a command, to the left of the blinking cursor icon, this right here is the folder name for the currently active folder. Make sure that your currently active folder is the desktop. So in my case, it's the desktop. It's c/users/my-username/desktop. The default on Windows when you open the terminal, let me go ahead and open a new terminal to show you guys. So here we go. I gotta zoom in here. So the default location is your user folder, your username folder. So to get to the desktop from there, you would type cd, which is the command for going to a directory. And then you would type desktop. And then that takes you to the desktop. If you're starting out from a different folder, that may not work, because what it's doing is it's looking for a folder inside your current folder named desktop. If you are starting out from somewhere else, then you can put in an absolute path, which is what it's called when you start out with the drive letter, and that will definitely get you there. So no matter which folder you're in right now, like if I just cd just a random, if I go to the drive folder and then cd, I think I have one called AAVSO net data or something like that. Yeah, so now I'm in some random folder on my computer. If I want to get over to the desktop, I would just type in the full path, starting with the drive letter, and then the users folder, and then my username, and then the desktop. And then that would take me back to the desktop. So my first advice to the person who's having trouble running the webinar script is make sure that your terminal is navigated to the desktop, as well as your webinar script being there. Assuming that that's true, and that you're right here, your terminal's on the desktop, your webinar script is here, and you're trying to run it and it's not working. I noticed that you said you saved as a text file. To be honest, I don't know whether the .py extension is necessary. So let's go ahead and test that out. So here's my webinar script, and it's named .py. I'm going to rename it to .txt and just see if that works. So now it's a regular text file. All the code is still in there, and we can see if we open it up. Yep, there's all the code. So I'm going to type in Python webinar script.txt. Okay, it looks like it should be able to run, even if it's a text file. However, make sure that you are typing the file name in exactly. So don't type in, now if I type in this Python webinar script.py, there's no file called webinar script.py anymore because I named it to .txt. So this wouldn't work. So just make sure it matches your file name exactly. And then if you're still having issues, I need some more detail in order to be able to troubleshoot. So put the exact error in the chat. Okay. So I noticed that Patrick Kavanaugh said he can't use copy paste. Patrick, could you put some clarification about where it is you're trying to copy? Are you trying to copy from within your terminal on your computer, or are you trying to copy the example code that I put in Zoom? I need some extra info on that. Okay, so does anyone have any questions about any of this that I've just covered about using loops, this sort of thing, or list comprehensions here, which are like loops that build lists? Any questions about that? Or about the Astropy table reader, or about running Python using a script file instead of in the command line. You know, last call for those kind of questions. Okay, it looks like we don't have any more questions on that. So now I'm going to show you guys one more example. This one will try to make a little bit shorter, but I want to show you one of my very favorite features here, which is a function, not a function, a package called Astroquery. Now, if you're the kind of person who gets excited about big data, like the Gaia DR3 data set or Sloan Digital Sky Survey data, and any kind of large public data set that you can use for data mining, you're about to be thrilled to death by the Astroquery package, because seriously, this is the coolest stuff. So I'm going to go ahead and pull up the Astroquery docs just to show you. Astroquery is highly related to Astropy. It's technically a separate package, but it's really, it's like an extension of Astropy. It will give you your results in the form of Astropy tables, and as it says, it's a coordinated package of Astropy, so they work really, really well together. And what Astroquery can do is it can make remote queries to astronomical databases all around the web, and then automatically download that data to your computer right into your Python session for you to play with. So one of my favorite ways to use Astroquery is for the Viziar, for access to Viziar databases. So let's go ahead to Viziar. Now, if you've never been to the Viziar site before, I'm going to go ahead and put the link here in the Zoom chat. So Viziar is a like a great big database of entire astronomical catalogs. So like here, Gaia DR3 is one of them. VSX is one of them, the AAVSO VSX. You might not have known that, but if you search VSX here, you'll come up with a fairly up-to-date copy of AAVSO VSX. I think it's updated once every couple months or couple weeks, along those lines. And there's kind of, I mean, it's almost ridiculous the amount of data that's available. Here I'm just running a search for spectroscopy, and it's going to come up with, yeah, see it found 2,343 catalogs that had the keyword spectroscopy in them. So there's a lot of data out there for people to sift through. If you're interested in data mining, this is a gold mine here on the Viziar site. But the form is honestly, it's kind of clunky, and it's can be hard to figure out how you're supposed to get your data set to play with. So like here, let's go look at Gaia DR3. And if you're like me, it would take like 15 minutes to figure out where you're even supposed to go to access the data on this page, because there's no form here. Right here, query Viziar tables, this button right here, that's what you're actually supposed to click on. And then that takes you to, oh, wow, there's a lot of tables to query. And I guess I should go with the main one, and I'm not looking forward to filling out that form. So what we're going to do instead is we're going to download some data from Gaia DR3 into Python. So I'm going to run through this example a little bit faster than I have done the others, because this is a little bit of advanced class stuff. So the number one thing that I'm using Viziar here, that I still use the Viziar website for, even though I am going to access it through Python, I'm going to copy down the dataset ID, or the catalog ID of Gaia DR3, because I know I'm going to want to query from it later. So whenever you find a catalog that you like in Viziar, you'll see a number, or I guess number's not right, sort of like a folder name almost. And that's the catalog ID. So here it's capital I /355 /Gaia DR3. And that's the identifier that you'll want to use in order to query your catalog remotely using Python. So I'm going to copy that identifier and then go over to my code. Now I'm going to go ahead and save this as like our first webinar script, but then make myself a new Python file for this. So let's say query Gaia dot py, and then I'll edit it with Notepad++. All right, so our catalog ID that we copy pasted, there we go. Let's go ahead and store it. Now we're going to want to import Astroquery so that we can do fun stuff with that. Astroquery split into a bunch of different folders depending on what type of remote site you want to use. We're going to be using Viziar, so let's go ahead and say from astroquery.viziar import the Viziar object tool. Does it have a capital? No, I think it's like that. And then I'm also going to show you a quick example with Simbad. That's another service that you can query here. So from astroquery.simbad import Simbad. Okay, so now let's say that we want to get some data on NGC 7789. That's a cool cluster I was looking at earlier. Carolyn's Rose cluster, I believe. So let's go ahead and find out the coordinates for that, because I definitely don't have those memorized off the top of my head. One way to find out the coordinates would be to open up your browser and go to Simbad and put in the Simbad search bar NGC 7789 and then do your search. However, you can also do these kind of searches from Python. So let's do that. Let's do salt equals Simbad.query object. And then let's put in the name of our object that we want to know stuff about, NGC 7789. And then print result. And I'm hoping that I remembered the syntax for this right. All right, so I'm going to save this as query Gaia.py. We're not querying Gaia quite yet, but we will in just a minute. And I'll go run my script in the command line. There we go. So what our Python code just did was it went and it pinged Simbad for us with our name of our object, which it input as main ID here. And then it came back with a whole bunch of other data. Doesn't all fit in the console here, but we could check by looping through the table or doing some of that other stuff we were doing earlier. Two of the things it returned, it looks like it returned an RA and a DEC. Perfect. That's what we need. So we want to use those coordinates to query Gaia. So we'll capture them using, how about Astropy's coordinate package? Astropy.coordinates import skycoord. This is a really useful object for representing coordinates in Python so that you don't have to do a bunch of weird math in order to, use coordinates, because astronomical coordinate systems are weird. And another thing that's useful when you're working with coordinates, astropy.units. Actually, this one would just be, there we go. So now I can reference anything inside the Astropy units module with the shorthand U. And I'll show you why that's useful in just a moment. So target, just call it target coord, equals skycoord. We'll put in the RA, which it looks like that was just called RA and DEC in all caps. Okay, so we'll put in RA, DEC. And then we'll tell the skycoord, because there's so many different systems, it's best to tell the skycoord explicitly, hey, I know that the coordinates are, in degrees, or that they're in hour angle or whatever. So in this case, if we look at the coordinates, This is in hours, minutes, seconds, so that would be hour angle. And this is in degrees, minutes, seconds, so that counts as degrees. So let's put in u.hour angle. And this is getting a little long, so I'll make that wider. U.hour angle, u.deg for degree. Okay, so that's a little bit long. Let me break it down. We're going to store the coordinates of our target as a skycord object. We took the SIMBAD result, pulled the RA and the DEC out of it, and then told the skycord object what kind of units to use. All right, now we have our coordinate, so we can go ahead and query VisiR with that coordinate. Now, technically, I believe you can query VisiR with an object name too, but I wanted to show you guys the skycord object. So let's say that Gaia result equals VisiR dot query. I forget the exact query call. All right, this is where it's good that I made notes in Visual Studio Code. Let's go look at how did I do that? Query region. Okay, so that's the function to query VisiR, query region, and we'll query at the coordinates of the target. Maybe let's make the radius, what do you say, 0.2 degrees. And then catalog equals catalog ID. All right. And yeah, that gets long awfully fast when you have a large font size. Okay, so now we have our Gaia result. Let's go ahead and save the script, run it here. Now I'm going a little bit faster now, but like I said, this is more of the advanced class, so we're gonna speed through it, and you can always review this recording later. So here it gave us back a table list. It had a result from Gaia, and it said it returned 50 rows. Now, that sounds a little bit low for a great big cluster like NGC 7789. So here's a good thing to know when you're using astroquery.visir. It does have a default row limit built in, so that you can test out your queries without worrying about accidentally querying VisiR for like every star ever observed by Gaia, and then it freezes up their servers, and then you'd feel bad about that. So they do have a row limit in place. Honestly, what happens is that your query times out, I guess, and they have protections for freezing up their servers. But anyway, it has a row limit. In order to change the row limit, you just type visir.row limit in all caps, and then you can set it to whatever value you want. If you set it to -1, that takes off the row limit. So it'll return as many rows as it can before it times out. So now I've changed the row limit. Let's run it again and see how many rows it comes back with. There we go, 12,000 stars this time. That sounds a lot more reasonable for a huge cluster like NGC 7789. All right, so getting close to the end here, we have our result here from the Gaia catalog. Why don't we go ahead and plot it? So first of all, what kind of columns have we got available? Let's try checking by printing the call names. Oh yes, and looking back here, you'll notice it says it returned a table list instead of a regular table. That's because it can sometimes happen that you put in a catalog identifier that matches more than one catalog, and then it will return a table for each catalog. So we, just like with the FITS file, where we had to pull out the first HDU, we're going to go into this table list and pull out the first table. So how about let's make that Gaia data equals Gaia result. And then I'll print the Gaia data call names, and let's see what we have to work with. Okay, there we go. That's our list of call names. And then I know what kind of graph I want to make. I want to make a color magnitude diagram. And I can do that using this Gaia data by using, let's see, here we have the G magnitude. Okay, we can use that as a kind of a proxy for absolute magnitude because we're looking at a cluster. It's all at the same distance, so that works out. And then over here we have BP minus RP. So that's like the B minus V color, but for Gaia. So I'll go ahead and pull in that data and make a plot. So let's try, we're going to make it a scatter plot. And uh-oh, I forgot to import Matplotlib. Let me add that up here. And I'll scatter the Gaia data G magnitude versus the Gaia data BP minus RP color. Actually, I guess I want the BP minus RP to be on the x-axis, so I'll put it first because Matplotlib always considers the first parameter to be the x-axis. All right, so if I throw in a command to show the plot, let's run the script and see if it works. We get a color magnitude diagram. And indeed we do. It's upside down because of the whole magnitude convention thing, of course, that we ran into that before, but here's our color magnitude diagram. All right, and we can zoom in because this is an interactive plot. I'll show you how I zoomed in. See this button down here. So we can zoom in, get some closer view of the main sequence here. And of course, I can do all the same tuning that I did before, like plt.gca.invert y-axis. I can do that. Now, you notice that the points were kind of crowded together. One way that you can deal with that is by making them smaller using the S parameter, which means size. So let's say that I want the size to be 1, which is smaller than the default. And there we go. I'd say that color magnitude diagram is looking pretty good. Okay, well, I think that that just about covers it for giving you guys examples of how to use some of the most popular Python packages for astronomy. We've gone over basic usage of Python. We've gone over Astropy, which is very useful for handling astronomical data. That's the #1 good thing it's good at, but it's also good at other things like coordinates. You can cross-match 2 catalogs together using Astropy if you ever have the need to do that. We have gone over NumPy, which includes a lot of extra mathematical tools for when regular Python doesn't have quite the power that you need to do some of your fancy equations or anything like that, or even if you just need a faster way to compute an average. NumPy can do that. We've also gone over Astroquery for using that for data mining of remote services, including Simbad and Viziar, with this example of a beautiful HR diagram from Gaia. And we've gone over Matplotlib for displaying your results as beautiful graphs. There are so many configuration options in Matplotlib, it's not even funny. You should read through the docs sometime if you're interested in making beautiful graphs. Okay, so with that, I'm going to finish my official demonstration and go over to questions. I think that we do still have a few minutes here, so has anyone got any questions about what all you've just seen? All right, I see that Timothy posted an error message into the chat. Yes, okay, someone would like to see the code that we just wrote. And this I will also copy paste into the chat. There you go. Okay, so taking a look at that error now, Timothy. Huh. Okay, so good news, Timothy. That error that you got there, what that means is that when you went to go clean the fainter thans out of your magnitudes, there actually weren't any fainter thans. So whichever light curve you picked a one that was particularly clean to start with. There were no fainter than observations. So just for the information of everyone else here, Timothy got an error when running our second example script, the one where it was plotting a light curve. He got an error where it pointed to the line of code that said if less than sign in observation magnitude, and it said that's not iterable, which is a really weird sounding error when you first get into Python. What that means in this context is it's not a string. So it expected to be able to check whether there was a less than sign inside of the magnitude. And it can do that if it's a string or if it's a list or if it's anything else that it can run a loop on. But you can't run a loop on a single number. So in this case, it wasn't a string to start with. It wasn't text to start with, right? It was just a number. That's why it caused an issue, because it turned out there was no need to clean up the fainter thans in the first place. It outputted numbers. Okay, so let's see. I'm just going back over the chat. I have not been reading the chat for questions so far, but I am just scrolling through it real quick right now. See if I missed anything important. No, it doesn't look like there were any absolutely pressing questions posed there. All right, that's good to know. Okay, so I do see that we had some people having issues copy pasting from the chat. So what we're going to do is actually publish these scripts, which we've been working on today. I'm going to add some annotations to these scripts. I'll show you one I've been working on here in Visual Studio Code. So this is sort of like a written version of my presentation. It's not going to be exactly the stuff that I said, but it covers the same general points for each of these 3 scripts. So they're not quite done yet. Like I said, I was sick earlier this week, and so I got behind on quite a few things. But once they are done, I will see if I can have them included in maybe the AAVSO communications email going out next week, or in a different email, so that you guys have written versions of these scripts with explanations to go back over and read through. So do be on the lookout for that. If you're interested in being able to go back and read an annotated version of this stuff, that will be published. In the long term, we would like to find a dedicated home. You know, right now our preparatory Python guide is just on the webinar series page, but in the long term, we'll try to find a dedicated home for Python related educational stuff at the AAVSO. But I don't have any word on where that's going to be yet. Okay, and it looks like that may be it for questions. If anyone has a super burning question that you want to post, now's the time, and I'll get to it when I'm done with these announcements. But I have one more announcement I want to make regarding educational materials. And that is one that you guys are probably thinking I'm getting to be a bit of a broken record here, but our Introduction to Python guide, I threw this together, and it copies, or it covers all of the basic Python info that you need to know to write Python code. It doesn't cover the astronomy specific stuff. That will be covered by this, this webinar just covered that, and the scripts that will be published soon, those will cover the astronomy specific stuff. But just the basics of using Python, how to install it, how to use the command line, how to use a text editor to write Python code, and then all the basic features of Python that you can take advantage of. All of that is in here in our Introduction to Python guide. And this guide, I've put the link in the chat a couple times. Here it is again. Right now, you can find it by going to the webinar page. So if you go to aavso.org/2022 how to hours, and those words are separated by dashes, and you'll get to our webinar page, and there's a link to that PDF, Introduction to Basic Python. So please do review that if you're interested in learning Python. If hopefully today's webinar gave you a good start, but if you find yourself with some specific questions later on that you weren't able to think of during the webinar, and then later down the line you're like, oh, I wonder how that works, there's a good chance it's covered in this guide. It's a pretty long guide. Okay, so looks like that's it. We did have one question here from Paul York asking if I will be available for follow-up questions. Unfortunately, I can't make any promises about that. I'm right now working 2 jobs and doing college, so I kind of don't have a lot of extra time for emails. So to make it easier on me, I would really appreciate it if you could try, whenever you have a question, try doing a bit of research yourself first. You'll probably learn lots of extra stuff about Python that way. If you get really, really stuck and it's just blocking you from doing any Python stuff, sure, you can reach out to me. I'm Herrington at aavso.org, and I will try to help you. But do try and exercise your self-research skills first. Okay, looks like that's the last question. So thanks so much, everyone, for sticking with me through this very long presentation. I hope that it was helpful. And don't worry if you missed some parts, if you started to fall behind somewhere. That's normal when we're covering this much material this fast. You'll be able to go back and review the recording and the educational materials to catch up where you left off. All right, let me go ahead and switch over the screen share to our ending slides here. Okay. All right, I'd like to close today's how-to session with a few quick AAVSO related announcements. First of all, I'd like to give a huge shout out to both of our sponsors, without whom this webinar series would not be possible. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer support, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served includes fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, our favorite, astronomy. Okay, good news for everyone. Today's webinar was recorded, and if you would like to review it immediately, you can do so on the AAVSO Facebook page. You can find us on Facebook under the username American Association of Variable Star Observers. Spell it out. Before too long, the recording will also be added to our extensive library of educational webinars archived on YouTube. You can find us there on YouTube under the username AAVSO HQ. So keep an eye out for that. This was the first of 3 webinars in our How to Python mini-series. Next month, we're going to be covering how to do asteroseismology using Python with a really promising webinar from Dr. Keaton Bell, who wrote his own Python package just for doing asteroseismology. He's going to go over that as well as the popular package LightCurve. So that should be a really great one. Make sure that you're practicing your basic Python so that you're able to follow along during his webinar. And he talks about asteroseismology and LightCurve analysis. And then we're going to cap off the year with a presentation from Dr. Eva Laplace, who will be presenting a package that she created for visualizing MESA stellar evolution models using Python. And that one looks very interesting. So those will be the next 2 webinars in our How to Python series. Make sure that you keep an eye out for registration for those as well. Okay, getting close to the end here. While you are here, we would be very grateful if you would consider making a donation to the AAVSO. Every single donation matters and goes towards making webinars like this one come to life.